And yeah, I started recording. And hello everyone, both in this meeting room and those people joining us online. It's a pleasure to welcome you to join this SFP events. Today we are honored to host Dr. Min-Chong Law, who earned his PhD from UQ in early 90s, and with Korean span over 30 years. And Dr. Law has a lot of experience from public health blog from Hong Kong health authorities to MTR station to airport terminals and super high-rise buildings and even Beijing Olympics projects. So today, Dr. Law will sharing his experience on design challenge of large metro station international airport terminals, and he will discuss the gap between the scientific research and practical design application, and how engineering can use its existing model to solve the complex problems. He will dive into fire smoke models and providing practical solution for each stage of the smoke development. Now, with further ado, let's give a warm welcome to Dr. Law. And Dr. Law, the virtual stage is yours.
Thank you. So is that everybody can hear me?
Yes.
Okay, thank you. Thank you very much for inviting me to give this presentation. I'm happy to share some experience in the past years when we do a design of project. The talk will focus on the smoke model and their applications, and this will fit to the theme of fire safety of complex buildings. For related to design, we have tools for fire safety design, like CFD models. FDS is very popular, and everybody knows this software and use this software. And also have zone models like CFAST. I know in Australia and New Zealand have a different zone models for performance-based design. But the CFD model and zone models normally are used for assessment to assess if the design is acceptable. That's particularly for the, it's called performance-based analysis. For other tools is like semi-empirical models. What we said in old days is for hand calculation or spreadsheet, but actually it's too complicated by hand calculation, because in many cases they have a transient state. So we normally use spreadsheet. These empirical models include the plume models, stratification models to estimate how far away the smoke can raise up, and ceiling jet model that's developed by Abbott in early 1970s, and also have models to estimate smoke spreading underneath the flat ceiling. Delegasius has developed a model in early 1980s. For the plume model, we have a number of plume models, but I have listed here with 4 very popular plume models when we use it to calculate the smoke production rate for the specification of smoke extraction fan. In the past days, when we do the practical design, we encounter some problems, like the plume models estimate smoke production rate and the capacity of smoke extraction fan. But the model discrepancies between them and the accuracy is not clear. And the stratification model is available from the literature, but calculate the maximum height of the smoke can rise, but cannot. This model cannot cover all the design scenarios. For the smoke reservoir size, this led to the ceiling jet and smoke spread. In the regulations, does not consider the factors that strongly affect the movement of smoke in the reservoir. That includes the ceiling height, the shape of the reservoir, and temperature of the smoke when the smoke spread in the reservoir. So based on this, so here is a simple sketch to show how a plume model, a smoke plume will develop. So we have a fire on the floor. The combustion products with the heat will rise up, and the fresh air entering into this hot air and form a plume. When this plume hit the ceiling and the smoke will turn around, it will form a ceiling jet, and then smoke will spread underneath the ceiling. If this ceiling height is too big, the smoke may not able to rise to the top, and the stratification could occur. At the early stage, the plume model is developed using a very small heat source. It's called point source. But for real fire, it have an area is much bigger than the point. So to correct the correlation of the plume model at early stage, Haskasted introduced the virtual origin to represent a point source and make use of the plume model developed in the early stage. So from the experience in the past, we have found the research of fire science established mathematical model or semi-empirical models. This model cannot be used directly for your project, particular project, in many cases. So they have gap between the model established by scientists and the application in practice. So engineers are required to fill the gap for the practical design. So in many cases, we can encounter. The fire engineers can make use of the existing model, like an empirical model developed by scientists. But we need to further develop this model for the design to take into account the specific project and also the limit of the regulations. So in the past years, in the performance-based design for large complex buildings, we have find a problem for the plume models, smoke stratification, and the smoke spread for long tunnel or large extended spaces. So this talk will systematically discuss the process of solving these issues and how engineers use the existing model for the practical design solutions. So following the smoke plume development and smoke spread sequence, so this talk will give some idea of the plume models, the smoke stratification, the ceiling jet, and the smoke reservoir. For the plume model, as mentioned before, they have a number of plume models used to calculate the smoke production rate. And this situation actually is causing confusion for the consultants, design engineers, authorities, etc. So many years ago, more than 15 years ago, the question has been raised regarding these models. So which model should be used for the system design and how reliable are these models? So this is a question raised from the clients to me many years ago. The story behind this is we have worked on a large metro system that includes tunnels and a few stations. The company I worked is an international consultants company. We have in early 2000, Hong Kong office is very, very busy. I leading a team here. We actually have engineers to support us from USA, UK, and Australia. In each of these countries, they have regulations recommend different plume models. And based on their experience or convenience, so they use their own model when they come Hong Kong to support the Hong Kong team and to write the fire analysis report. So these 4 models, actually the last 3 has been used. And the first one is a has-casted model, is basically the basic of all these 3 models. At least 2 of these two models are based from the has-casted model. This one, has-casted, developed these models in late 1970s and early 1980s. And at that time, NFPA introduced the plume model for practical design. And these 2 models, actually, the NFPA model is basically the same as casted model, but dropped the virtual origin point. So these are the same term, and this term, this constant is actually the results of this one times 0.026. You can get 0.0018. So this is the same equation, but dropped the virtual origin. The reason is what the NFPA said at that time is the virtual origin is normally very small. It's only applicable to the plume fires. But for real fire in buildings, virtual origin is not very important. But actually, this is not true. Later, we can see the difference because of the influence of the virtual origin. A SIPS model is for UK, recommend for a SIPS guide E. And this is also the same as has-casted model, but drop the second term in this bracket. And Thomas Hinckley model is based on the published data for large fire source. But this model have no heat source, but use the perimeter of fire to replace the heat source. So this also causes many problems because we don't know the heat source, and it's difficulty to determine what is the perimeter of the fire. But from the experiments, the large fire, Hinckley and Thomas claimed this correlation is better fit for the large fire source experiment compared with other models. So I think this correlation is popular in Australia or New Zealand. Use different models in the same project, different part of the project. I got a call from the project manager of the clients, ask me to explain why the same company use different models to estimate the smoke extraction rate, and which model is right, and what is accuracy of these models. So this question is very simple, but it's confused me as well. So I went into the detail, the reference for detail of all these three models. And here we compare these four models directly, plot into these four figures. We can see this correlation is a smoke production rate. This is the fire size or the heat release rate with different smoke clean height or ceiling height. That's 3 meters, 5 meters, 15 meters, and 10 meters. That's cover a wide range of smoke heat release rate and also wide range of smoke clean height. You can see the difference is very significant, particularly for NFPA and Hesse-Kassett. We mentioned before, is the only difference is dropped the water origin. You can see the difference. This is Hesse-Kassett with the water origin. This is NFPA model without the water origin. You can see the difference is quite big, particularly when the fire getting larger. So all other smoke clean height give similar results. So they do have influence from the water origin and also other parameters. To further investigate the difference of these four models, what I tried to do is I use the SIPC model as a basis, the SIPC model as a basis, and compare with other three models, Hesse-Kassett model, NFPA model, and the Hinckley model. This is a typo here. It's H, not N. Rearrange this equation. If all these models predict the same results, so this ratio should be 1, but actually it's quite different. So this is the results compared between Hesse-Kassett and SIPC model. We can see from here, if the results are the same, we should have a straight line across this 1 here. But in reality, is for all the smoke clean height, for all the fire heat release rate, the Hesse-Kassett model give a conservative assessment. We say have a higher smoke production rate, we need a higher smoke extraction system. So this is a conservative, give a conservative results. If compare the NFPA model with SIPC model, we can see for small fire and smaller heat release rate, the NFPA model give a conservative results, but for large fire size and higher smoke clean height, the NFPA model give a less conservative compared with the SIPC. Because if you have draw a line here, this 1, and the part of the curve are below 1, part of the curve belong over 1. The reason we missed this part, the curve, is because this part is the flame height larger than the smoke clean height. So the plume model is not applicable. And compare the Hinckley model with the SIPC model, the situation become more complicated. But we can still see in most of cases, the Hinckley model provides conservative results compared with SIPC model. In summary, if we think the full range, what we assessed from the heat release rate from 0 to 10 megawatts, the smoke height from 2.4 to 15 meters, this is a wide range. And compare with SIPC model, the difference between the 4 of them is from -10 to positive 28%. This is a difference, the discrepancies of these 4 models. But in practice, we normally have the design require smoke clean height higher than 2 meters. So if we take 3 meters here, and the design fire, the heat release rate should be more than 3 megawatts. The actual differences of these 4 models, the range of discrepancies from -5 to 20%. In the practice, when we use these plume models to calculate the smoke production rate, we normally apply a safety factor of 1.2, so provide 20% additional capacity for the extraction fan. So if we take this into account, this will recover this 20% difference. So if we consider this difference with the safety factors, we may conclude 4 of these models are applicable to estimate the smoke production rate for specification of smoke extraction fan. So this is a very roughly conclusion, but it solved my problem to answer the queries from the project manager of our clients during that days. With this assessment, we actually have done some experiments, but this experiments is not purely designed for verification of these 4 models, but is a hot smoke test. The requirement from FSD for atriums higher than 12 meters in Hong Kong. So any space higher than 12 meters, FSD will request, authority will require the hot smoke test. So we have a hot smoke test in one of our projects with the atrium height more than about 35 meters. We use Australia standard to configure the fire, the heat release rate with a 1 A0 tray plus 1 A1 tray with a fire heat release rate is about 1 megawatts. During the hot smoke test, we installed the thermocups in 2 locations. The one is one location, the level is 11 meters. Another one is 20 meters. So we measure the temperature. This is the measured temperature, and the smoke temperature can actually calculate it from the heat balance with the plume models. Because QC we can calculate from the plume models, and then we plot all these results together, compare with the experiments. We can see this straight line is from the model, and this curve is from the experiments. We can see the predictions is reasonable close to the measurement. We can see, you can possibly see the difference is quite big, but you can, if you have a look at the real temperature, this is a 34 degrees, this is a 38. Actually, the difference is less than 5 degrees. This from the high atrium. And another test is from in PTR, is Passenger Transport Exchange Center, is 12 meters tall, and the thermocups installed at a 10 meters level and 7.6 meters level. We can have a similar results. So as I mentioned before, the test is not specially designed for verify the model, the plume model, but we make use of this measurement, compare with the model prediction, give some kind of some level of confidence of the model prediction. But this, because the measurement is very rough, and the environment, the test condition is not well controlled. So the test results, we cannot say 100% reliable. And because currently we revisited this data and put this in the paper, and this part has been criticized by the peer reviewer. So we are still working on it, how to do additional experiments to adjust this issue. So this is part one. Now we move to the smoke stratification part. With the smoke plume rising, the fresh air surrounding will enter into the plume. With the plume rise up, the mass and volume of smoke will increase. The temperature will going down, will be reduced. So when the smoke rise up to some level, the plume temperature will reduce close to the environmental temperature. And then the smoke plume possibly will not rise anymore. It will possibly stop there, and then the stratification could occur. So this is a figure to illustrate the situation. If we have a very tall atrium, with a possibly small fire, the smoke rise to some level, possibly will stop. If the smoke not rise up to the top, the smoke detection system, detector will be not activated. If normally the smoke extraction system is activated by the smoke detector automatically. If the detection system not work, the smoke extraction system will not work. So the whole stratification will affect the detection system, the smoke extraction system. So this is a problem. And the issue was raised with this project. This is the Hong Kong International Airport Terminal 1. That's over 20 years ago, opened 1997. If you have been in Hong Kong, you know where it is. This is an airport terminal, and this area is a check-in hall. On this side is airport express station. The people drop from the road, actually use this bridge. This bridge go to the check-in hall. And here is arrivals hall, is called greeters and meeters place. From this arrivals hall to the roof, the height is over 20 meters. I'm not sure the exact height, but it's over 20 meters, possibly below 25. And on the top of here, in these places, actually have a mount the aspiration smoke extraction system with a small point in this area. So during the later stage of the design process, the actual construction is nearly finished, but still not in operation of the airport. They have a question raised by authorities, both from the fire authority and the airport authority. Their question is, can smoke rise up to the roof and activate the detector and start up the smoke clearance system automatically? Here I have 2 points I like to explain to you. Is the Hong Kong Airport Terminal 1, I think other Terminal 2 and Terminal 3 are the same. This is not talk about the smoke control system, because smoke control system were based on the design fire size heat release rate to calculate the smoke production rate and then specify the extraction system. The fan actually specify the capacity of the fan. But the smoke clean system is not to provide you a smoke clean height based on the plume model, but to clean the cold smoke after fire. This is a difference between the smoke clearance system and the smoke control system. And also in Hong Kong Airport, the heat release rate from a fire in the public area or in the circulation area is less than 1 megawatts. So this is the Hong Kong airport terminal requirement. So any furniture or equipment placed in the circulation area need to have a assessment, make sure the heat release rate from that piece of furniture, the fire sites, the heat release rate will be less than 1 megawatts. This is a very restrictive requirement because in Beijing and Shanghai airport, we designed basically the circulation area, the fire heat release rate is 5 megawatts. This is because the airport needs to place some commercial areas like kiosks with about 9 meters square. But for 1 megawatts, you cannot put any commercial activities in the airport. So if you in the Hong Kong airport in Christmas time, you can see the Christmas tree are all made with metal, not the real, even not plastic, not the real tree. It's all metal Christmas tree. That is the reason. The first question is if the smoke can rise up to the roof with that big of fire. And also a question is how long the smoke will take to reach the detector in winter. Because in winter, the Hong Kong weather, the temperature is around 20 degrees. And the air condition control, the airport manned area is about 24 degrees. So in winter, basically the whole airport have been a uniform temperature environment in terms of fire condition. So in winter, in summer, how long the smoke will reach the detector to activate this, the detectors. In summer, for the energy saving issue, the terminal building, the manned area temperature was controlled 24 degrees. But on the roof level, the temperature is, the design specification is 55 degrees C. That's in summer. So in summer, the smoke rise up is in a long uniform or ununiform temperature environment. So with these questions, so we went to try to find a solution to answer the authorities' queries. So basically, in NFPA 92B and SIPC have recommend or list a stratification model. This is a correlation. HM is the maximum height the plume can rise. QC is everybody know is a convective part of the fire source. And this DT or DH is the temperature gradients. From this model, we can very easy to calculate how high the smoke can rise up with a positive temperature gradient. However, because the power here is minus, if the temperature gradient become to 0 and they have no solution of this correlation, even if this temperature gradient become negative, so even more difficult to get the results. So to answer the authorities' queries for the uniform temperature environment, so we have to find a way. So where we can start? So we tried different references and literature from literature. So now we came to Dougal Drysdale's an introduction to fire dynamics. In that book, they have a correlation is center line gas velocity of the plume. This correlation actually is a McCaffrey's plume model. McCaffrey have a set of equations to express the performance or the characteristics of the plumes. So this is one of them. UO is the velocity of the plume center line velocity. Q is the total heat release rate. H is height, the location we are looking for, and others are constants. So with this equation, we rearrange it because the velocity, center line velocity, can be replaced by dH over dt. That's a very simple math. We all know this math, and rearrange the equation and put the constants in, and then we have this correlation. We can simply integrate this equation from 0 from the floor to the roof, and time will be from 0 to t, and then we have this very simple correlation. We did not make any assumptions, but purely from the McCaffrey's center line plume model velocity correlation, we can have these results. So from here, we plot the situation for a uniform temperature environment for our airport terminal arrivals hall. So this curve show you a 20-meter ceiling height. This is all from 20 meters height. For 20 meters height, this gives the heat release rate from the fire, and this curve is tell you how long the smoke will rise to a certain height. Take this as an example. At this point is about 1 megawatt. It's 100 kilowatts. Is 0.1 megawatts. Is very small fire. The smoke can actually rise to 20 meters in this is about 8 seconds. So this is a very quick. Even with a very small fire in the uniform temperature environment, smoke can rise up to 20 meters very easily. Plot B is a fixed 1 megawatt fire. This is the smoke, the time for smoke rise to some height, and this correlates the ceiling height. The height varies from 0 to 60 meters. We just arbitrarily pick this point is say 45 meters ceiling height. The smoke can rise to 45 meters up in about 10 seconds for a 1 megawatt fire. So for 1 megawatt fire, in a uniform temperature, the 1 megawatt fire the smoke can rise to a very, very tall roof easily. So this is for uniform temperature environment. So we have these results. For the long uniform temperature environment, because long uniform temperature environment we can actually use the NFPA recommend correlation. But because we already started for the uniform temperature environment, so we tried to get some solutions from the first principle of physics. So this is a correlation. This is a inequality from Dugu-Dressteyer, but actually this is from the first principle of physics. Cp is heat capacity of air, and this term here is actually the mass, the flow rate, the mass flow rate across the plume section here times the temperature difference. the average temperature difference, the plume temperature over the ambient temperature. This is actually the energy. This energy, if all the convective heat from the fire source are close to section here, actually this is the equation. This can be an equal sign. But because this is a QC, for further development using the central line correlation from McCaffrey's plume model, we need to use Q. So we still use include here. We replace the velocity with dH and dL, but here is the average velocity, not the central line velocity. We need to pay attention here. And also the temperature here is the average temperature of the plume average plume temperature over the ambient temperature. So everything put it here, we can make sure this inequality is still on hot. Another assumption is we assumption B is the size of the plume at the location of H from the point of the fire source is proportional to the height. So this is also is basic assumption for the plume model with the virtual origin at the very beginning. So we have not include any additional assumption. So this inequality is still on hold. So based on this, we have further developed is for our case, because we have a lower part temperature is TA is 24 degrees C, and the top, the ceiling level or the roof level temperature is 55 degrees C. But here we assume the temperature gradients, the variation of the temperature against the height is constant. So this assumption will be easily come out with this correlation. So TA is a bottom temperature, top is 55, and the T log is the location at the middle, anywhere H away from the fire source. So we can have this correlation. We replace this correlation to the equation here, and then we can have a rearrange. We can have this equation. And the reason we arrange in this way is because later we can know the central line correlation from McCaffrey's plume model expressed in this way. We need to make use of that correlation. But that correlation, Tm, is not for average plume temperature, but the central line temperature. So here we replace Tm, the average temperature, with the center line temperature. And we also introduce a constant B into the inequality, inequality, and become the inequality becomes an equation. And now here, the only possible error introduced into this inequality is replaced Tm with T0. Actually, Tm and T0 have a correlation from Tm19. Tm is equal to T center plus TA, T local, the local temperature, divided by 2. But I tried to use that correlation. It is very difficult to solve out this equation later, because they have no relationship available, or the relationship cannot relate to McCaffrey's plume model. So we place this, possibly will introduce some errors into this equation. So based on that equation, now we introduce the McCaffrey's correlation. This is the central line equation with this is on the temperature at the center relates to the total heat release rate and H, and also the ambient temperature are related to the center temperature and the fire heat release rate and H. So with these two correlations, replace to the equation before, and then we have this equation. This equation, we can get the time for smoke raise up to some height or to the roof based on the heat release rate and the height, the temperature, the top temperature and the lower part temperature. But the problem here is that we need to determine the constant B, because constant B we introduced in the middle, but we don't know what is the actual value. So this the constant here have puzzled me for quite some time when we try to solve this problem. I thought maybe we need to use the experiments, but experiments will be very complicated. There are so many variables. If the constants are unknown and all other known variables are become a variable, because it's a long value become a variable, it just impossible to do experiments to determine the constant B. But when puzzled me sometime, I thought for a long uniform temperature, because we have a lower part temperature and the top part temperature are different. If the top temperature equal to the same as the bottom temperature, and then it become a uniform temperature environment. And if for the uniform temperature environment, this integration term become to 0. And for the uniform temperature in situation, from this long uniform temperature equation should give the same results as the uniform temperature we resolved before. So both will give you the same results. So based on this connection, we can actually get the constant very easily. So the air heat capacity over the constants equal to 12. So that's very simple. And so we replace the constants B, and then we have this equation. So based on this equation, we can actually plot the line here. Of course, for plotting time against the height, using this integration term is also complicated when at the early stage when I plot this curve. But now in recent days, when we revisit this part of the work, we have a student help me to plot it. He actually find to plot this curve from the website is when you input the variables, very easily to get the results. So this is a plotting from the students helped me. It's very similar to what I plot 20 years ago. I spent a lot of time to plot the line. So come back to here. So this is a curve to have plotted the situation for different ceiling height with the various temperature from 24 degrees C from the bottom to the top 55 degrees C with different ceiling height. Like this is for 50 meters, 20 meters, 25 and 30 meters, 30 meters. Like we choose 30 meters as an example for discussion. Now here is about 0.7 megawatts is 700 kilowatts fire, 30 meters roof height. For the smoke will take 2 minutes to rise from the floor to the roof. So that's 2 minutes is quite long for smoke detection. And here, for 1 megawatt fire, it will take 1.3 minutes rise to 30 meters high, 30 meters roof height. 1.3 minutes is still quite a long time. So in summary of this analysis, so if for 1 megawatt fire with the temperature varies from 24 to 50 degrees, will take 10 seconds to 15 meters high, 20 seconds to 20 meters, 40 seconds to 25, and 1.3 meters to 30 meters high. So because we are not measure the smoke stratification, the smoke stratification can only estimate by observation. So if we assume if the time for smoke rise to a height larger than 1 minute, the smoke stratification could occur. Because for smoke detection system, if the detection system be activated by more than 1 minute, it seems a little bit too long from a common sense. So in this case, the smoke stratification could occur at 25 minutes height. So 25 minutes height will for one, possibly the smoke will rise up to 25 minutes in 1 minute if the fire less than 1 megawatt fire. So the results show the environment temperature, and also the results show the environmental temperature significantly affect the smoke rise up time. So this is the assessment from here. If we go back to the long uniform temperature, the correlation recommended by NFPA, apply to the case here, we can actually estimate the maximum height the smoke can rise is 26 meters with 1 megawatt fire. So this is very close to the assessment by the equation we developed from McCaffrey's correlation. But this correlation cannot be used for the uniform temperature when the temperature gradients equal to 0, that I've mentioned before. So now we're back to the case start this issue to answer the authorities' queries. So in winter, for a uniform temperature environment, the smoke can rise up to the roof within 20 seconds very easily, even with a very small fire. For summertime, if the fire less than 1 megawatt heat release rate, the smoke might rise up to, may not rise up to roof, and the smoke clearance system needs to be activated by hand, because the authorities' major concern is how this system can be activated. So our conclusion is if in summertime, if very small fire, we need to activate the system by hand. For a fire larger than 1 megawatt fire, the system can be activated automatically, very likely, because 1 megawatt, over 1 megawatt, the fire smoke can rise up to 20 degrees, 20 meters roof in less than 1 minute. So this is the conclusion based on our assessment to answer the queries from the authority for a very practical problem. Now, I think we need to move quicker. We run out of time. For the we go to the ceiling jet and the smoke reservoir. for the smoke spread in on this underneath the ceiling, we have different situations like unconfined ceiling, flat ceiling with no restrictions, with the plume raise up and hit the flat ceiling. Smoke, ideally, smoke will spread circularly underneath the ceiling space. If the smoke reservoir is unconfined or have no smoke reservoir. For confined, in general, the smoke reservoir should have a boundary or smoke barriers. So in many cases, we have rectangular smoke reservoirs. The smoke will, if the smoke plume or the fire is placed at one end of the smoke reservoir, smoke will rise up to the ceiling, spread horizontally with circle, and then hit the boundary, and smoke will force to spread in one direction. So this is ideally, it's just an illustration. The smoke possibly will not spread in this way, but this is the situation we simplified, and it is for our analysis. They have ceiling models, ceiling jet models developed by Albert in early 1970s. So the first set of equation is related to how far the smoke can spread from a flat ceiling, unconfined flat ceiling. And the left-hand side is actually the boundary conditions for the equation on the right-hand side. The boundary conditions is express the situation of the smoke exit from the turning section, because the plume rise up vertically, hit the ceiling, and then turn around, spread vertically. They have a section particularly defined as a turning section. So when smoke get out of the ceiling, the turning section form a ceiling jet, and this is a boundary condition from the Albert model. And replace this boundary condition into this equation, we can actually plot the curve to see how smoke move under a flat ceiling, without confinement. This set of equation is also the Albert model to predict the temperature of the smoke. When the smoke move from the ceiling, move underneath the ceiling, the smoke temperature will cooling down along the movement. So these equations will give the temperature of the smoke, actually the front line of the smoke. So this is close to the plume, and this equation is for the distance away from the plume. And from these two equations, the first set of equations plot how far the smoke can move. From the fire safety design point of view, we normally design a smoke clean height. The required smoke clean height is, say, 1.8 meters in Australia. Normally we use 2.2 meters or even higher. Here we actually, we assume we require a 2-meter smoke clean height. Here is a different ceiling height. What we try to say here is for a 4-meter ceiling height, if we require a 2-meter smoke clean height for safety reason, the smoke can actually spread 16.6 meters. The smoke can actually spread up to this point. The smoke will drop down to 2 meters. From this figure, we can actually have a 865 meters square. smoke reservoir, a circle. So if we have a circle of with a radius of 60 meters, we only have about 800 meter square smoke reservoir. If we have a 6 meter ceiling height, the smoke can move 33 meters to here. The smoke will reach 2 meter height. So the smoke reservoir can up to 3,500 meter squares. So if we have a 3,500 meter square circle, the plume, the fire placed in the center of this circle, we can have a smoke reservoir more than 2,000 meter square. The 2,000 meter square number is actually the regulated value. The regulation gives this number is actually arbitrary number. If we consider the ceiling height, we consider the safety factor, the 2 meter safety requirement, we can have smoke reservoirs less than 2,000. If the ceiling height is low, we can have a larger smoke reservoir if we have a higher ceiling height. So this gives us, I think, is the smoke reservoir shouldn't be regulated with the arbitrary number and should consider other issues like the ceiling height, the smoke temperature, and the shape of the smoke reservoir. So this is the reason we do this study. And for the temperatures, the reference from literature say if the temperature of the smoke 5 degrees over the ambient temperature, the smoke clean height, the smoke clean smoke layer can maintain on the ceiling level. So from the second set of Albert correlation, we can actually estimate the temperature of the smoke when the smoke spread in the reservoir. We're not going to the detail in this part. The reason, the story behind this assessment is from a very large depot from Hong Kong metro system. This depot is the biggest depot in Hong Kong, possibly not the biggest in the world, but biggest in Hong Kong. The depot area is this shape. The total area is over 250,000 meters square, is 225 hectares. It's very big. And in this depot, the whole depot has to be smoke controlled. The reason is on the top of this depot, around this depot is a huge property development. But for our analysis, is focused on the center of this part. This is a stabilizing area with 400 meters long and 110 meters wide, is rectangular. And because the Hong Kong regulation required 2,000 meters square smoke reservoirs, it cannot be larger than that. And that caused a lot of problem for this depot's design. I have in this depot give a little bit more detail of the depot. It will give the reason why we need a larger smoke reservoir. Underneath this slab, there's a 25 hectare slab actually covered by, fully covered by a concrete slab. The concrete slab is also 25 hectares. So underneath the concrete slab, they have a trencher. The service trencher is 2.5 meters deep. In these trenches, they have services, pipes, cables, and many services in the trencher. And the trencher, this trencher has been, we come it later. This trencher every 40 meters have one drencher. And this is a picture when the depot is finished. This depot, because the depot is very long, is more than 700 meters long with more than 200 meters wide. So you can see the height of this depot is seems very slow, very small, but actually height is about 11 meters. And this is the plan of the depot. On the top of the depot, there a huge development with a sports ground, with the schools, hospitals, and elderly houses on the top of the depot. And around this depot is also houses and development. This is the inside of the depot after finish. You can see the services dock here. This is the drencher with a 2.5 meters top. We like to use these drenchers as a smoke barrier. And this is a picture I get from the Google Earth. This is the current situation of the development on the top of the depot. The depot is about this height. On the top, they have car parks, shopping centers, and the high-rise residential buildings. And the more details here. So this is about 400 meters with a width of 110 meters. So the drencher, every 40 meters have a drencher. So what we try to say, try is to make use of the drencher wall as a boundary of the smoke reservoir. And we make the smoke reservoir is 40 meters wide with 110 meters long. This is more than 4,000 meters squares. And then we don't need to use additional smoke barriers in the center to divide this large smoke reservoir into less than 2,000 meters square reservoir, because there are a lot of services in the middle. And to solve this problem, we simplify this smoke reservoir into this figure. If we have a fire started at the end of this reservoir, smoke will spread from one end to another end. We have a H. We have a smoke clean height 2 meters. Actually, this can be because for the case we here is actually 6 meters smoke clean height. We have a H with the smoke spread along the reservoir. And to investigate this case, we actually find a reference from literature. Delegations have done a very similar work with these two equations. But when I plot these two equations with the situation we met for a 20 meters width channel, like a 20 meters channel, we find a problem. When have a plot this curve, when smoke travel about 10 meters, they have this continuity point here. This shouldn't happen because the smoke is flow smoothly. They shouldn't have a discontinuity. Another problem is here when the smoke travel over 20 meters for a higher ceiling height, like 6 meters, the smoke temperature actually is higher than the lower ceiling height. This is a conflict with our normal observation because the lower ceiling with the lower smoke clean height, you should got a higher temperature. So that gives us another conclusion is the delegacies model, the model from literature developed by fire science, cannot be directly used for the specific cases we meet for this project. So now we're back to revisit the Albert ceiling jet model. So this ceiling jet model, this is for the low close roof cross plume area. This is for the far distance away from the plume. So we start from this equation, we rearrange it into with our variables here. We did not make any change, just rearrange the equation. But here we need to introduce, because this is a confined ceiling, smoke will be confined in this channel and spread in one direction with the rectangular channel. So what we did here is we introduce an equivalent radius REQ to replace the radius R. So make sure the area of smoke covered this ceiling are equal. So this is a very simple correlation from replace the radius with REQ here and replace into the equation, and we can simply integrate this equation and can get the simple expression here. The assumption of use the equivalent radius to replace the R for the unconfined ceiling cases is we assume the heat loss from the smoke to the ceiling and environment is proportional to the smoke coverage. So if we have a smoke cover the same ceiling area, the heat loss should be the same. So this is the only assumption applied into this equation. So based on this equation, we replot the case we plot for the daily gases model. We can see here the discontinuity point disappear, and also the temperature, the higher ceiling height temperature, we got a lower temperature. This is a consistent with what we observed in many cases. So for further justify this model, so we actually find out some experimental data in early 1970s from UK classicals test. They have a 2 megawatts, 4 megawatts, 8 megawatts fire. The fire test is in a very long unused rail tunnel with about 600 meters long. And we make use of this data, compare with the model we developed from Albit model, and also compare with the daily gases model. So this is daily gases model. These 3 lines is by the model we developed, and this is experiment data we get from literature. So the experiments data, this comparison give us some confidence of the model we developed, provide a trend of the temperature measurement. So this is for 2 megawatts fire. This is for 4 megawatts fire. They have 1 point here is for 8 megawatts fire. So the model we developed give a trend, but the daily gases model is underestimated the temperature of the experiments. But in close to the fire, all these both the model we developed and also daily gases model underestimate the smoke temperature from the measurement. So we apply very quickly. We apply this analysis to the case we designed to apply for 4,000 over 4,000 meters squares smoke reservoir. So from here we have a 5 megawatts and 6 megawatts fire situation. The prediction temperature for smoke travel for over 100 meters. The temperature still over 40 degrees. So the temperature prediction give us the confidence that smoke clean height will be maintained. this figure, this gives the smoke clean height. Their smoke clean height getting higher and higher. The reason is we have the smoke extraction system in operation. They have 5 or 6, 5 extraction points. So every extraction point extract the same amount of smoke. So when the smoke passes the extraction point, the next smoke will spread further. So the smoke clean height will keep increase. So this is the results. And now very quickly to summarize, I don't think we need to give any summary here. But the one point I like to address here is if you are still studying in university or work in as a consultant, as an engineer. So there, in many cases, you possibly will find problems need to be solved, but they have no solutions, no existing solutions available. You have to find your own way to resolve the problem. And the most important is to find where to start. Once you have a starting point, you have a clean thinking, and then with some hard work, and then you will have solutions. I think I possibly have run for too long. If I have any questions, I'm very happy to discuss with you here. Thank you very much, and thank you for inviting me to give a talk here.
Thanks for such great presentation. Not only you explain how you develop those equations and like in very detailed way, but also you kind of connect the with real projects. So I feel like I don't know, is anyone feel like the same way? I get involved with a lot of projects in Hong Kong in just an hour. So yeah, I personally really like the presentation. So we start with like, is there any question from online? And we got around 10 minutes for the question sessions. Or we give some time for those audience online to come up with some question or typing your questions, or if you feel like, you feel free to unmute yourself. And do we get any question from the room? Just feel free to ask as well.
In practice, sorry.
I will actually got one question from the meeting room.
Okay.
Hi, yeah, thank you. Thanks a lot for the wonderful presentation. It was very insightful because I think, yeah, in the professional world, yeah, we don't think sometimes going in this deep level or like thinking ahead. And
okay.
So this was actually a kind of eye-opening for us as well. So one of the questions currently with the introduction of the CFD models, are FAIR engineers actually going into this basic concepts and charting from the fundamentals, or they just directly utilize the CFD models and come out with the solutions?
Okay, that's a very good question. But I mentioned at the beginning, for the CFD model or zone models is very popular, and a lot of, particularly the CFD model FDS is every FAIR engineers use FDS in these days. But for design of smoke extraction system, the extraction rate or how big the fan you need for a building, you either specify based on the regulation. They give you some kind of method to calculate the extraction rate, or use the plume model are introduced here. You use a plume model because you know the smoke clean height. You can calculate what is the smoke extraction rate you need. But the CFD model don't give you this figure. The CFD model asks you the heat release rate as an input to estimate or assess if your design is safe. Basically, if you have a smoke extraction system there, you need to specify what is the fan's extraction rate, what is the fire size, and then you do the number crunch with the FDS and tell you, this is not okay. You need to increase the smoke extraction rate, or you need to specify a different fire size, and then you justify. But for the design at the beginning, you need to tell the system engineers, or in Hong Kong it's called building services engineers. Tell them you need to specify that big of fan to size your fan room. So at the very beginning, you need to tell them. So you still need the plume models. So this is very basic, and start with the project.
All right. So
the CFD model or zone models, you can do the detailed analysis to tell the authorities, or this design is okay. They tell you the people will be safely evacuated based on this condition, but not for design, not for the design. So design and assessment, there are some difference.
So I think, like, as a starting point, in stages of the projects, this might be a good approach for fire engineers. Later stages of the project, maybe we can go into the details CFD.
Yeah, that's true. Yeah, I think there's some echoes in the system. But I know what you said.
Yeah, because I have mostly seen people directly starting with CFD, and as you have mentioned, like, we define the fire size and put an extraction rate, and then do a trial and error methods.
Yes, but possibly you when you get into the fire engineer get into the project, but that project is already far away from the starting point. I think if at the very beginning, people are normally in many cases, particularly in Asia countries, because specify the fan capacity is, you don't need to use a plume model. The regulations give you parameters like each square meters, what is the extraction rate for 1 square meter, then you time the total smoke zone area, then you got the total extraction rate to specify the fan capacity. But for fire engineering design or performance-based design, we can start from the design fire size, the heat release rate, and use the plume model, tell the engineer what is the smoke extraction rate is needed. And then for further detailed start, you can use FDS, CFD model, and other tools to do the assessment.
All right. Yeah. Thanks a lot. Thank you.
Thank you. Thank you for your question.
All right. Thanks, Dr. Law. And any last minute questions from online? All right. Yeah, just thanks. Right.
Thank you.
Yeah. There's a question from Audrey. So, yeah.
Hi, Dr. Law. It's amazing presentation, and I realized there. So, for example, like the plume fire models, when applied to the different national codes, it's always do some simplification. So that makes a lot of difference when we compare to the Hasadesk fire model. So I think it's a very good way to discuss about the difference and give the constant to discuss about make the design more conservative. But when we discuss about the ceiling jet and the smoke, it's obviously like a Hasami localized fire. It's always give us a very like a clear definition or limitation, which kind of building or compartment you can apply it for. I think here it's also some mathematic problem when we try to apply this kind of theoretical models to very modern projects, like have a very high entrum and a large space. So my question is thinking about like, rather than we just try to discuss and to use these kind of models, is there any way like we can improve and make this kind of theoretical model could be widely applied in more situations?
Yeah, I think this is a quite a big question, but in many cases, every project have a different situation, and here I present 3 cases to solve 3 different issues, like the smoke, the stratification. I believe that the model we developed here for stratification can apply in any case. But for the smoke spread in a channel, in a rectangular channel, is purely based on a rectangular, and assume the fire placed at the end of the channel, and then do some mathematical analysis. This is only applied to this case. If you find something else with a different shape of the reservoir, possibly you need to do a different ways. But the idea here is the experience I try to share here is engineers, you possibly everyone will find something you need to solve, but you cannot find a solution, an existing solution, or the no solution available. You need to do something yourself. But the most important is you need to find the starting point. Like at least 2 cases, we find the starting point from McCaffrey's plume model. Use the center line plume correlations, and this is need some thinking, and also need some a little good mathematical knowledge to do something. But when you particularly like I said, determine the constants, it struck me for quite a few weeks. I keep thinking how to find that the constants apply to that equation. But when you find the way to resolve it, it's very simple, actually. So the clean thinking is very important. Once you find the way to solve the problem, and I think the problem is already being half solved. Mm-hmm. But if you say the equation can apply to a very wide range of situations, is difficult. That's the case depending. So some cases you possibly apply for many different scenario, but some others only apply for one scenario. The purpose is, particularly for the performance-based design, we need to find something innovative, and we'll also need to convince the authorities. This is a major purpose.
Thank you. It's a very good insights, and thank you for sharing.
Thank you.
Thanks. I will get one more question from online, and the audience want to know, is it possible to apply such models for fire resistance assessment? Obviously not considering the radiative heat flow to the structure.
Yes, actually, I do have cases for fire resistance, but for fire resistance, I think Nanzu is much better than me. And we do have cases at early stage to do the calculation for the fire resistance for steel structures. And I think there are many cases in structure fire group in PolyU, and Lanzhou is a good one to start with.
All right. I think we're about to finish. All right. I actually had one more question.
Just a last question, because I was thinking about this rectangular smoke reservoir, because we fire engineers involved in the initial stages of a project will not be knowing the internal layout, especially like what will be coming at ceiling level. For example, there might be like some service lines passing through, and these are some obstructions which we don't take into account in our calculations initially. So does that actually come into our, or are we actually capturing that in our safety factors, like 1.2 safety factor that we have mentioned? Does that take into account these kinds of obstructions which can actually have an effect on the movement of smoke?
The discontinuity, you are talking about the discontinuity of the, okay, see. The obstruction, are you talking about this curve?
Yeah, but my question was, it's related to this, but it's also general in the sense like.
Okay, the obstructions in the smoke reservoir is not considered, and that's even more complicated. And for that part, if you want to solve to see what is obstruct in the reservoir effect the smoke spread, that part do need a CFD model to do the simulation. And for the discontinuity here is basically the Delegacy's model is developed with a nano corridor, is about 3.5 meters wide, but we apply this into a 20 meters wide channel. So this is over their model's limitation. So that is the reason. So I skipped this issue. And for the safety factor is actually for the smoke extraction calculation for the plume models. That's for normal practice. When have a plume model to calculate the smoke production rate, we normally give a safety factor is 1.2. That's in practice in Hong Kong. I think in Australia as well. But in some cases, possibly the authority ask you give 2 factors there for a small fire. That's also fine, because the smoke extraction fan sometimes can be very big with the small smoke reservoirs.
Thank you. Thanks a lot. Thank you. Thank you for your time.
Thank you.
Thanks, Dr. Law. I would just want to thank you giving this presentation using your public holiday time. And
thank you.
And maybe in the near future, like you always welcome to not visit. Well, you always welcome to back to the University of Queensland. You got us. Right.
Thank you.
All right. I think we're kind of already running out of time, but thank you again, and have a nice day. Thanks to giving this presentation.
Thank you very much. Have a nice day too, and we hope we can revisit UQ and see you guys there.
Yeah, looking forward.
Thank you. Bye.
Bye, everyone. Thanks, Dr. Law.
Thank you.